Hello friends, I welcome you in lecture number 6 on interpolation. So far we have discussed about finite difference operators and their relationships. From this lecture onwards we are going to discuss different interpolation methods. We have seen what is the meaning of interpolation in lecture number 1, but we just recall the definition or meaning of interpolation before starting this lecture. As we have discussed in lecture number 1, that suppose we have some function of x denoted by say y, and we don't know that what is the formula of fx, that is explicit formula of function fx is unknown to us, but we are given some values of function at different values of independent variable x. For example, suppose values of x are x0, x1, x2 and so on xn, and corresponding values of the function are denoted by y0, y1, y2 and so on up to yn. That means this y suffix I denote the value of function at point xi. So we are just having these table values or this data, and using this data, suppose we are interested in finding value of function fx at some point which is in between x0 and xn. Using this information, what is the information? We know that value of function y equal to fx at x0 is y0, value of fx at x1 is y1 and so on. In general, at point xi, value of function is given denoted by yi, and we are having these values for only these n plus 1 points. You can see that we have n plus 1 points starting with x0 and ending with xn. And using this information, suppose we are interested in finding value of function fx at some point x which is in between this x0 and xn, then the process of finding this value of fx at the point x between x0 and xn using these table values is called interpolation. Interpolation is the process of finding value of function fx at some point x between x0 and xn, where we have these values of function at points x0, x1 up to xn. So we have different methods of interpolation in different situations, and using those different methods we are going to solve this type of interpolation problems. So what is the idea of interpolation methods? So interpolation methods will find the polynomial denoted by p of x or sometimes pnx, which is having degree less than or equal to n. Because we have n plus 1 points, we will have a polynomial of degree less than or equal to n passing through all these points. That is, value of pn, this polynomial at point xi is equal to yi, and value of function at xi is also yi. So this function fx and polynomial pnx agree at these n plus 1 points. Value of polynomial at x0 is also y0, and value of function at x0 is also y0. Similarly, value of polynomial at x1 is y1, which is nothing but value of function at x1. So the idea of interpolation is to construct the interpolating polynomial which satisfies this condition, that is value of polynomial at xi equal to value of function at xi and I equal to 0, 1, 2 up to n. And using this polynomial we will find out the value of function at point x which is in between x0 and xn. We don't know what is function fx, we are not having the formula of function fx, but we will find out the formula for interpolation polynomial denoted by Pnx, and using this interpolating polynomial we will estimate the value of function at point x, where x is in between x0 and xn. So this is the main idea of interpolation. We have to construct the interpolating polynomial which agree to the given function at given points, that is value of polynomial at x0, x1, x2 up to xn, and value of given function or value of unknown function at x0, x1 up to xn are same, represented by this relation, that polynomial at xi equal to value of function at xi I equal to 0, 1 to n, and using this polynomial we will estimate the value of function at point x which is in between x0 and xn. So we have different methods of finding this interpolating polynomial. We are finding the polynomial, and that is known as interpolating polynomial. And if we have n plus 1 points, the degree of this interpolating polynomial is at most n, that is degree of interpolating polynomial is n or less. So we have different methods of finding this interpolating polynomial, and we will start with this method, Newton's forward difference interpolation. We are going to discuss 4 interpolation methods in our syllabus. We will concentrate on 2 types of interpolation methods. One type of interpolation methods are called general interpolation method, and here we have specific or particular interpolation methods. What is the difference between general and specific interpolation methods? So in some situations, some interpolation methods assume that the distance between any two successive values of x is same, or difference between any two values of x is equal, that is x1 minus x0 equal to x2 minus x1, that is equal to x3 minus x2, and so on. Or we can say that the space between values of independent variable is same. In other words, we have equally spaced values of independent variable x. In general, we can write that xi plus 1 minus xi equal to some constant, say h, where I is 0, 1, 2 up to n. In other words, values of independent variable are equally spaced. So if we have equally spaced values of x, then we have 2 methods of interpolation known as Newton's forward difference interpolation and Newton's backward difference interpolation. But suppose values of x are not equally spaced, that is they are unequally spaced. So in that case we have general methods. One is Lagrange interpolation and second is Newton's divided difference interpolation. We will discuss all these 4 interpolation methods one by one, but these 2 are general interpolation methods. Lagrange interpolation and Newton's divided difference interpolation are general interpolation method. They can be applied to any set of data, either values of x are equally spaced or unequally spaced. But this Newton's forward difference interpolation and Newton's backward difference interpolation can be applied only if values of x are equally spaced. That means difference of any two consecutive values of x is same. So we will first discuss these 2 methods, Newton's forward difference interpolation and Newton's backward difference interpolation, with the restriction that values of x are equally spaced. After discussing these 2 methods, we will see general interpolation methods, which are Lagrange and Newton's divided difference interpolation. So in this lecture I have concentrated on Newton's forward difference interpolation, and here we assume that the distance between any two consecutive values of x is constant, and that we denote by small h, I equal to 0, 1, 2 up to n. Or in other words, we say that values of independent variable x are equally spaced. We will require the idea of forward difference. We have discussed about forward differences in earlier lectures. We just recall, suppose we have this type of data, we are given n plus 1 values or n plus 1 points corresponding to x0. Suppose value of y is y0, y1 corresponds to x1, then y2 and so on, yn. Here we have to go up to xn. These are the values of independent variable, and these are the corresponding values of y, which is a function of x. Now we have defined forward difference in this way. Forward difference is denoted by delta, and if we have delta fx, then that is going to be f of x plus h minus fx. Now suppose I am interested in delta of xi, then or forward difference operator at point xi. This is forward difference operator at any point x, but suppose we are interested in the forward difference at point xi, then that is given by f of xi plus h minus f of xi, and we have denoted f of xi by yi. Therefore this is going to be f of this point will be f of xi plus 1, and this we will denote by yi plus 1. So in these notations, f of xi is yi. This is the definition of forward difference. This is called first order forward difference. Similarly, we can define this second order forward difference. Suppose we have delta square yi, then that is going to be delta yi plus 1 minus delta yi. So this we have discussed in detail in previous lectures, and here we are going to use these forward differences. We will find out the first order forward differences, second order forward differences, and as per our requirement. Suppose I am interested in the forward differences corresponding to this data which are of first order, then y1 minus y0 is denoted by delta y0, then difference between y2 and y1 is denoted by delta y1, and so on. Yn minus 1 is denoted by delta yn minus 1. So in general, remember this definition, delta yi is yi plus 1 minus yi. Now to apply this formula, we assume that values of x are equally spaced, that is xi plus 1 minus xi equal to h. We are given this type of data, we are given some values of function fx at given values of independent variable x, and suppose we are interested in finding value of this function fx at some point x which is in between x0 and xn. Then we will first find out this quantity. We are interested in the value of y at point x. This we want to find out. So we will use that value at which we want to find out value of function fx, and we will subtract first value of x from that value, and we will divide by equal distance between any two successive values of x, and we will denote this quantity by small p. So first we will find out value of small p, which is x minus x0 divided by h, and we will remember the formula of Newton's forward difference interpolation polynomial. Polynomial is denoted by Pn x, and the formula for Newton's forward difference interpolation polynomial is Pnx equal to y0 plus P delta y0, where P is x minus x0 upon h, plus P times P minus 1 divided by 2 factorial, here delta square y0. Then you can imagine the next step, here P minus 1, then P minus 2, and here 3 factorial. If I have 2 factorial, I am writing second order forward difference. Here I have 3 factorial, so I will write third order forward difference at y0. And you can see, if I have 2 terms in the product, in the denominator I have 2 factorial. Here in the product I have 3 terms, in the denominator I have 3 factorial, and here I have written third order forward difference. So in general, suppose I have n factorial here, then I must have n terms in the product. So we are starting with P, and P minus 1, P minus 2, and I have to extend up to which point. So that you can imagine from this. If I have 3 factorial here, I am subtracting up to 2. If I have 2 factorial here, I am subtracting up to 1. So if I have n factorial, I will subtract n minus 1 from P. And here I have n factorial, so this is nth order forward difference at point y0. So this is the formula of Newton's forward difference interpolation polynomial. Using this polynomial, we can find out value of this polynomial at any point x, and where x is nothing but x0 plus ph. This you can rewrite in this way also. Now we are interested in the value of function at point x. So we will consider this value of interpolation polynomial at point x as the estimate of required value. So at whatever point we are interested in evaluating the value of function f(x), we will find out value of Newton's forward difference interpolation at that point x, and we will consider this value as the estimate of this function value at point x. So all you have to remember is that you will be given this type of data in table form, and to apply Newton's forward difference formula, you have to first check whether values of x are equally spaced or not. If they are equally spaced, then only you can apply Newton's forward difference formula. Then you determine, or you find from the question, that at which point x you are interested in finding the value of function. So using that point, you find out this quantity given by P equal to x minus x0 upon h. x0 is the first value of x in the given data. H is the distance between any two consecutive values of x, which is same. After that, you remember this formula of Newton's forward difference interpolation polynomial, and then you substitute value of x everywhere in this formula, and you will be able to find out the required estimate of given function at a given point. So this is very easy. I have taken one problem to explain this. This I have written systematically. Suppose we have the following values where y is a function of x and values of x are equally spaced, that is xi plus 1 minus xi equal to h, I equal to 0, 1 to n. So this is given data. Values of x are x0, x1 up to xn, that is n plus 1 values, and corresponding values of y are denoted by y0 up to yn, and because y is equal to fx, this yi denotes the value of function at xi, and we want to find the interpolating polynomial Pnx such that value of this interpolating polynomial at all these points equal to value of function at all those points. That means interpolating polynomial and function fx agree at given data points. Then we find out p using this formula x minus x0 upon h, and then we use the Newton's forward difference interpolating polynomial to find out value of polynomial at any point x, and we will consider estimate of fx as value of polynomial at point x. So here I have written if x is any point between x0 and xn, then value of y at x or value of function at x is approximated using this interpolating polynomial. So I have taken this example: compute cosine hyperbolic 0.56 using the following table values using Newton's forward difference formula. Here we are given different values of this cos hyperbolic function at values of x given by 0.5, 0.6, 0.7, 0.8. So here our function y is cos hyperbolic x, or we can denote this by yx also, and these points we can denote by x0, this is x1, x2 and x3, and corresponding values of y are denoted by y0, y1, y2 and y3. And using this table we have to find the value of cos hyperbolic function at point 56. That means we have to find out value of this function at point 56, and because we have 4 points, our polynomial will be of degree 3 or less. So using that interpolating polynomial we will estimate value of this cos hyperbolic 0.56. Now as I discuss what I will require, I will first require this forward differences. So whenever we have this type of problem, we will prepare the forward difference table, and using the definition of forward differences we will be able to write down the required forward differences. So here I have written these given values of x and y, and in this column I will write down first order forward differences, then I will write down second order forward differences, and then third order forward differences. These values are denoted by y0, y1, y2 and y3, and these values are x0, x1, x2 and x3. Now by definition, first order forward difference at point y0 is nothing but y1 minus y0. So we will subtract this y0 from y1 and we will obtain this value that I directly write using scientific calculator: 0.057839. This is nothing but delta y0. Okay, remember the definition of forward difference. If we are interested in delta yi, then that is given by yi plus 1 minus yi, or yi plus 1 minus yi equal to delta I. So here I am taking y1 minus y0, so I will use 0 suffix here, that is delta y0. Now what is this y2 minus y1? That will be denoted by delta y1. So I have to subtract y1 from y2 and I will get this difference as 0.069704. This is difference of y2 and y1. I will denote it by delta y1. Then difference of y3 and y2, that turns out to be 0.082266, and this is difference of y3 and y2, that we will denote by delta y2. So these are the three first order forward differences. Now we write down second order forward differences. So difference of these two, that is delta y1 minus delta y0, and if you recall, if we have second order forward difference at point yi, then it is nothing but difference of first order forward difference is delta yi plus 1 minus delta yi, and we are finding delta square y0. So using this, it is difference of delta y1 and delta y0. If I take I equal to 0 here, I will get difference of delta y1 and delta y0, that I will denote it by delta square y0. Similarly, if I have difference of delta y2 and delta y1, then that will be denoted by delta square y1. We are using this suffix. So in general, delta yi plus 1 minus delta yi is denoted by delta square yi. So first we subtract this quantity from this, that is delta y1 minus delta y0, and that is second order forward difference at y0, and that turns out to be 0.011865. This is nothing but delta square y0. Then we find out delta y2 minus delta y1, and that turns out to be 0.012562, and this is difference of delta y2 and delta y1, and that we will denote by delta square y1. Similarly, we can find out third order forward difference. For that, we consider this minus this, and that turns out to be 0.000697, and this is nothing but third order forward difference at y0. And because we have this x0 to x3, that is 4 points, our interpolating polynomial will be of degree less than or equal to 3. So up to 3, or we will have maximum forward difference is up to order 3. So here we stop, and now we are interested in these values only. You will see in the formula that we will require only these values: y0, then delta y0, then delta square y0, and delta cube y0. And to use the formula, first we have to calculate this quantity p equal to x minus x0 divided by h. Here we are asked to find out value of function at point 56, and value of x0 is 0.5, and you can see distance between any two successive values of x is 0.1. So this is going to be 0.5 and here 0.1, and this turns out to be 0.6. So we will use this value of p in the formula of Newton's forward difference interpolation. So that I have written here. Here we want to find out cos hyperbolic 0.56, therefore we take x equal to 0.56, h is 0.1, distance between successive values of x, and first value of x is 0.5, and p is x minus x0 by h, that is 0.6. Now Newton's forward difference formula is Pnx, that is notation for interpolating polynomial, is given by y0 plus p times delta y0, p minus 1 by 2 factorial delta square y0, p minus 1 p minus 2 by 3 factorial delta cube y0. So you can see here we are using forward differences at point y0, and that we have calculated here. This is delta y0, delta square y0, delta cube y0. Value of p is 0.6 and y0 is given in the table. Now we are interested in the value of function at point 56. So that we will estimate using the value of interpolating polynomial at x equal to 0.56. So in the next step we will put x equal to 0.56 here, not 0.6. Here I have to write 0.56, and that turns out to be value of y0, that is 1.127626, plus p into delta y0, value of p is 0.6, delta y0 from the table 0.057839, that we have substituted here. Then value of p 0.6, 0.6 minus 1, that is minus 0.4 divided by 2, and delta square y0 is put from the table 0.011865, that I have written here. Then p, again p is 0.6, p minus 1, that is 0.6 minus 1 is minus 0.4, p minus 2, that is 0.6 minus 2 is minus 1.4, divided by 3 factorial is 6, and here third order forward difference at y0, that is from the table 0.000697. So using scientific calculator, we find that value of interpolating polynomial at 0.56 is 1.160944, and that is our estimate for value of given function at 0.56. So this is the required value. We are asked to calculate value of cos hyperbolic 0.56 using Newton's forward interpolation. So that we have calculated here, and that turns out to be 1.160944. So you can see this is very easy. You just have to remember this Newton's forward difference formula, and you remember that how p is calculated, and while doing calculations you have to fix your calculator up to certain decimal places. Here values of this function are given up to 6 decimal places. Therefore I have done my calculations by fixing my calculator up to 6 decimal places. Sometimes they will specify that find the required value up to this much decimal places. In that case, fix your calculator up to required decimal places and then do the calculations. And be careful while doing all these calculations. If at least one entry is wrong, then you will get all the wrong values and your answer will be wrong. So this is about Newton's forward difference interpolation method, and in this method what is our restriction? We can apply this method if values of x are equally spaced, and if equally spaced values of x are given, then value of function at point x can be obtained by Newton's interpolation polynomial at point x. We are not getting exact value of function at point x, but we are approximating it using Newton's forward difference interpolating polynomial. And in the formula of Newton's polynomial, we will require value of p, that we will find using this formula, x minus x0 divided by h. So this is all about Newton's forward difference interpolation method, and in the next or upcoming lectures we will discuss remaining methods of interpolation. So I stop here. Thanks for watching.